Alright, so let's look at some linear estimation problems. So I have written up different problems here. So this is y is of course the data, and let's say x is the unknown. The way I have set up everything is whatever you see here is a random variable. In other words, this is noise. So we'll make the usual assumptions. The data and the noise are uncorrelated. So in this case, here in the second problem, you have two sets of data. One measurement is x plus n. The second measurement is n plus w. So this is an interesting problem. I'll explain this again. So this is the traditional problem. Signal in noise, find me the best estimator. So here this is a variation of this where the second one is a different take on noise, because you have the noise is scaled by another random variable, a. So again, once again, you can assume these two random variables are independent here. And in this problem, it's another take. So the question is, if you have these problems, what is the mean squared error, what is the best estimator, etc. So remember, this is the estimator will be whether it is scalar, or in this case this is scalar, it could be vector also. So in general, estimator is the best linear estimator is going to be a function of the data, and then error, which is in the linear case the error is orthogonal to the data. So this translates as expected value of epsilon y star is 0. But epsilon y star is expected value of x minus x star, which is hy multiplied by y star. So if you expand it, you get expected rxy, which is expected value of xy star, is equal to h multiplied by expected value of yy star. So this is ryy. So we get the standard expression. The unknown is rxy or yy inverse. So let's apply this quickly to all these problems. So in the first problem, it is a scalar. So we just need to compute rxy. So rxy is expected value of x multiplied by x plus n. Signal and noise are uncorrelated, so this is simply rxx. And ryy is, you can see from here, is simply expected value of x plus n the whole squared. And that's if signal and noise are uncorrelated. This is this is a scalar case, so I'll simply write it as sigma x squared. So this is sigma x squared plus sigma n squared. So in this case, the estimator h turns out to be sigma x squared over sigma x squared plus sigma n squared. And the most interesting thing is I'm going to call these errors sigma 1 squared is, so from here the minimum mean squared error is expected value of epsilon squared, but this is because epsilon is x minus x star and error is orthogonal to data, this is simply x star, epsilon x star. But this will turn out to be expected value of epsilon is of course x minus hy multiplied by x star. So this will turn out to be rxx minus h or yx star or rxy star. So if you substitute for, in this case, this is going to be sigma x. So this is the expression we'll be doing for all these problems. Minus sigma x squared, I substitute for over sigma x squared plus sigma n squared multiplied by rxy, which is once again sigma x squared. So you can see this turns out to be sigma x squared, pulls out sigma x squared, sigma n squared over sigma x squared plus sigma n squared, which you can write it as sigma x squared over 1 plus, or you pull out the noise term divided by throughout by sigma x squared, sigma n squared, then this would be sigma x squared divided by 1 plus sigma x squared over sigma n squared, which is the SNR term. And now if you go to the second problem, so that's what, so you can, if you want, you can write this as sigma x squared over 1 plus SNR, etc. So let's go to the second one. Here you have y is actually the two data sets, y1, y2. So this, of course, you can write it as in this manner. Y, n and n plus that. So here Rxy will be expected value of x multiplied by y1 star, y2 star. So if you plug this in, this will turn out to be so we can do it here itself. Y1 star is x plus n, and the other one is n plus w. So this would be, of course, sigma x squared, and these are uncorrelated, so you get 0. And ryy is sigma x squared plus sigma n squared. Here you have sigma n squared plus sigma w squared, sigma n squared, sigma n squared, because it is 2 by a matrix. And if you do the inverse, I'll just write down the results, so that the inverse will turn out to be 1 over sigma x squared, sigma n squared plus sigma w squared, plus sigma n squared, sigma w squared. Here you have sigma n squared plus sigma w squared, and sigma x squared, sigma n squared, minus sigma n squared, minus sigma n squared. And if you compute h, which is rxy multiplied by ryy inverse, this will turn out to be sigma x squared divided by sigma x squared multiplied by sigma n squared plus sigma w squared plus sigma n squared, sigma w squared. And here this will be sigma n squared, sigma plus sigma w squared minus sigma n squared, the second term. Now we need to find out the best estimator. So I'm going to call, in this case, the first problem x1 hat. So I'm going to call this x2 hat. This would be hy. So h is already computed. So the interesting thing is sigma 2 squared. So once again, if you compute sigma 2 squared, in this case, this will turn out to be sigma x squared, sigma n squared, sigma w squared over. So here over, let me finish this, sigma x squared multiplied by sigma n squared plus sigma w squared plus sigma n squared, sigma w squared. And this will, if you divide, this is, you can actually write this as in this fashion. So that's the error, and you can see it's of course less than sigma 1 squared. So this estimator is better. This estimator actually turns out to be, if you substitute the values, this will turn out to be sigma x squared, a constant in any case, divided by sigma x squared plus sigma n squared, sigma w squared over sigma n squared plus sigma w squared. But the interesting thing is what comes here, y1 minus 1 over 1 plus sigma w squared over sigma n squared multiplied by y2. So notice the interpretation of this. If you look at the data set here, so here you have a signal plus noise, and it looks like the second observation is a variation of this noise. So in many practical problems it is like this. A doctor puts a stethoscope on the heart, so he gets a noisy version of some valve. Then to figure out the noise, he moves the stethoscope somewhere nearby place, so that he only gets a version of the noise that's affecting the valve. So then of course he immediately puts it back on the original place, so that adaptively he can cancel out this noise from the second observation. And that's what is happening there also. If you look at this, the best estimator uses y1, and it adaptively subtracts a portion of y2 from y1. Notice that. So what the doctor does it over years of experience turns out to be the optimum estimator uses y1 data, and from y1 a portion of y1 is subtracted out, and you get a estimate. So this estimator is certainly superior to the first one, because the mean squared error is larger than the mean squared error for the first case. So the third one is also an interesting problem. So here of course you again x3 hat is some h3 y, and the y is of course y1 y2, a different y1 y2, because y is of the form x plus n and n. So here of course if you work out the details, notice that Rxy would turn out to be sigma x squared 1 0, and Ryy is sigma x squared plus sigma m squared. Here sigma a squared, sigma m squared, and there is no, so the inverse is easy. Inverse is simply going to be 1 over that. So if you plug in all these values, sigma 3 squared will turn out to be, so h is of course, so from here, so you can see when you multiply this with this, you are only picking up the, so the h3 will turn out to be, so I'll just write down the h3 result there. H3 will turn out to be, so we can see from this is sigma x squared over sigma x squared plus sigma n squared 1 0. So what this says is that it simply ignores the second data, because the best estimator is, as you can see, I'll write it down here, it's simply going to be only a function of y1, sigma x squared over sigma x squared plus sigma n squared y1. So it simply decides that the best estimator is discarding the second noise is, so the result is the sigma 3 squared is the same as sigma 1 squared, which is sigma x squared over 1 over 1 plus Sn. So here the other data did not help. So finally, equally interesting case is the fourth one. So this is the third one. The fourth one is where y1 is x plus n, y2 is x plus an. So there, the second version you have a multiplicative version of noise. So the question is that useful? So one needs to do it. So of course y is of the form 1 1 x plus n an. So if you work out the details, the ryy here will turn out to be sigma x squared plus sigma n squared, right? And this is sigma x squared, and the off diagonal entry will be sigma x. The second diagonal entry will be sigma a squared, sigma n squared, and rxy in this case turns out to be, you can see here, rxy is x with, so it's going to be sigma x squared 1 comma 1. Now if you substitute all this, I'll write down the result. H will turn out to be, of course, a constant sigma x squared over sigma x squared plus sigma a squared, sigma x squared plus sigma a squared, sigma n squared, multiplied by, so I'll write down the estimator itself. X4 hat is hy, which will turn out to be sigma a squared y1 plus y2. So we are indeed using some portion of y2, and if you compute the sigma 4 squared, that's the interesting part. I'll write down the result. So this turns out to be sigma x squared over 1 plus sigma x squared over sigma n squared plus sigma x squared over sigma a squared sigma n squared. But the interesting thing is, quickly you can see that this error is less than sigma 1 squared. In other words, having that even corrupted second noise is better than not having it. So even this estimator is superior to, I'll rewrite it here, sigma 4 squared is 1 over, or rather sigma x squared over 1 plus sigma x squared over sigma n squared plus another constant, which turns out to be sigma x squared over sigma a squared sigma n squared. And you can clearly see this is smaller than 1 over 1 plus or sigma x squared over sigma n squared, which was the noise corresponding to the, and the mean squared error corresponding to the first case. So even coming back here, even this is having a noisy version, and a second noisy version which is even inferior to this is superior to just having only one version of the noise. So here is the relative performance of these estimators. So this is superior to this. Having this data is actually in fact it ignores the data. So this problem is as good as this one. Here this data is useless, and this data is also superior. This second data is worth having it because you can reduce the error. Now of course if you want to compare this case and this case, you can compare it because you have sigma 2 squared and sigma 4 squared. Of course it will all depend on the value of sigma w squared versus the sigma a squared and squared, sigma n squared, etc.